Okie dokie, here we are. This particular PowerPoint is going to be about something called confidence intervals. And it's going to start a somewhat lengthy discussion about a variety of different confidence intervals. However, more broadly, this fits into a bigger picture of what we call inferential statistics, which is kind of like the second big half of this class. We talked a lot about descriptive statistics at the very beginning of the class, and now as we're kind of winding the class down, we're going to finish off by talking about something called inferential statistics, and this confidence interval is the first part of that discussion. So like I said, we have two sort of broad, somewhat distinct types of statistics. The first type we've already mastered, right? We've already mastered descriptive statistics, univariate and bivariate. We've learned about organizing, picturing, summarizing information in one or two variables. Then we went on maybe a little bit of a tangential detour, but an important one. This sort of gold-paved path of probability, right? We started by talking about probability. Why? Why do we care about probability? We care about probability because of random variables. Random variables were these sort of abstract ideas, remember? They were this sort of random phenomenon that takes different values with different probabilities. They have probability distributions, they have means, they have standard deviations. To be able to talk about a random variable meaningfully, we need to have at least a little bit of an understanding of probability. They are probabilistic constructs. Now, why do we care about random variables? We care about random variables particularly because of the normal random variable, right? Of all the different random variables out there, and there's lots, the one that we focused on was the normal random variable. And we plugged and we chugged and we drilled and we practiced some more. And why? Why do we care about normal random variables? We care about normal random variables because of wow, I can imagine like a beam of sunlight shining down from the heavens, sort of highlighting these three letters. We care about the normal random variable because of the CLT, because of the central limit theorem. That's why we care about the normal random variable. That's the whole point of our journey. The whole point of our journey has been a guided discovery of the central limit theorem. It was as strategic and as concise as could possibly be to be able to hopefully meaningfully talk about that. Why? Why do we care about the central limit theorem? Well, we'll see that the central limit theorem is the guiding motor. It's the engine that drives where we're going for this sort of second half-ish of the class. It's what we need for this idea of inferential statistics. Inferential statistics is what many people think of as, quote, real statistics. And what makes this work, again, the engine that sort of drives this, the mechanism that justifies it, is that central limit theorem. So let's talk a little bit about inferential statistics. The two broad types of statistical inference, or of inferential statistics, it can be broken into two broad categories. The first is confidence intervals, is what we're getting ready to talk about. We'll talk about it for a while. Then we're going to talk about something called hypothesis testing coming up after confidence intervals. So we're going to start by talking about those. We're going to move on, and we're going to answer every single possible question that you've always had, but have been too busy to ask regarding hypothesis testing down the road. So, to motivate the idea behind a confidence interval, which at its heart is a very simple, very intuitive idea, let's consider a random sample of 30 or more people. Say we look at their average height. What's the probability that the sample mean, that the average height of this sample will dead on equal whatever the true mean is? That is, I'm asking a little bit more symbolically, what is the probability that x bar, the sample mean, is equal to mu, right? That's that Greek letter mu that is our usual abbreviation for the population mean. Now remember, if my sample is 30 or more, it's a guaranteed fact
thanks central limit theorem, that the sample mean will have a very close to normal distribution. And remember, when we talked about normal distributions, we said there's this interesting fact that the probability that a normal random variable equals any number is always 0, which means that the probability that the sample mean will equal the true mean is just some number. We don't know what it is, but it's still just a number. The probability that the sample mean equals the true mean is 0, right? Which is maybe perhaps mildly disheartening, because the sample mean is supposed to be the best guess of our true mean. However, we're observing that it's extremely unlikely that it will actually equal it.
Nonetheless, despite the fact that it is extremely unlikely, in fact mathematically impossible, that the sample mean will dead on, precisely, right down to the 0.00000001 decimal point equal the true mean, it is nonetheless very likely that it will be very close to the true mean. We talked about that, right? We did a number of examples talking about this idea when we talked about the central limit theorem. We explicitly showed how we could use the central limit theorem to really say exactly how likely and exactly how close. We've shown that the sample mean is very likely to be very close. Nonetheless, it's not going to be it exactly. Now, in statistics, we go on and we quantify this idea of closeness with something called a confidence interval. That is something we've more or less already been exposed to. Every confidence interval has associated with it two things. It has a confidence level between 0 and 100, non-inclusive. You would never make a 0% confidence interval. You would never make a 100% confidence interval. But in theory, it could be anything between 0 and 100%. Now, even though in theory it could be anything between 0 and 100%, the most common ones done in practice are 90%, 95%, and 99%. And really, of those three, probably the most famous, the most conventional, the most widely used is 95%. So I believe that if you work for the government, say the FDA, for example, that you're mandated by law, you're legislated that you have to use 95%. And so many other non-government researchers, non-government statisticians, really the whole world of statistics, by and large, has really rallied behind, for better or for worse, this value of 95%. If it's good enough for the government, it's good enough for me. And so that's the one thing, right? They have two things associated. One's a confidence level. The second is a margin of error. Now, again, we've seen this before. We're just formalizing the idea that we already explored when we talked about the central limit theorem. Again, we said the sample mean is a good guess for the true mean. Why? It's a good guess because it's very likely to be very close. We explored both of those numbers in a number of examples. Now, when we talk about this idea of very likely, that's essentially the confidence. So when we say that the sample mean is very likely to be very close, how likely? Well, that's really this idea of confidence. It's how confident are we? And this idea of how close, well, that's essentially our margin of error. That margin of error is quantifying this idea of closeness. So these are the two sort of measurements that we've already talked about in our previous PowerPoint.
So how does this margin of error work? Again, it's a very, very intuitive idea. Imagine it's summer break. And you're with your parents, and they're driving you to grandma's house for a really crazy, wild, fun family getaway. And you're bored, and you look at your watch and you say, "Oh my goodness, how much longer until we get to grandma's house?" And your parents say 1 hour. Now imagine if you whatever, you pulled out an app on your phone, or you went to your watch. Imagine you set a stopwatch somehow. And you stared at it. You stared at that clock. You stared until it was exactly down to the second 1 hour. and then your little clock, your stopwatch beeped, and you got angry. You said, "How dare you, Mom? How dare you, Dad? I can't believe you lied to me. This is a betrayal that will never leave my soul. I will never forget this treachery. You told me that it would be an hour until we got to Grandma's house, and look, the stopwatch just beeped, and we're not there yet." To which, of course, your mom or dad would likely roll their eyes and accuse you of large amounts of melodrama, right? They would respond by saying, well, you need to understand that when people say 1 hour, they're not promising it's going to be exactly 1 hour. They're saying that it's going to be about 1 hour. And what's implied in that statement, what most of us understand without even taking a statistics class, what's implied in that statement is that there's a little bit of a fudge factor. There's a little bit of margin of error. What your parents really meant when they said 1 hour is they probably meant 1 hour, say, plus or minus 10 minutes, right? Because there's lots of factors they can't control. Whether or not traffic's bad, whether or not they happen to hit a lot of red lights, whether or not they get hungry and need to stop for food, right? All of these things could change, both shorten or extend the time that it takes, right? It's impossible. It's impossible for your parents to predict how long it's going to take to Grandma's house, right down to the second, just as we observed it's impossible for the sample mean to dead-on equal the true mean. So what do? In both situations, we take our best guess. In the case of your parents, that best guess was 1 hour. In the case of statistics, our best guess for the population mean is the sample mean. We take our best guess, and we add onto that a fudge factor. We add onto that a margin of error. We say, I'm within 5 minutes, I think. I'm within 10 minutes. I'm within 1 minute of the correct answer. Now, in statistics, right, we have a very precise formula for what this margin of error is. So, for a C% confidence interval, right, that C can be a number of values, 90, 95, 99, 98, 80, right, for a certain percent confidence interval, for an unknown population mean mu, when sigma, the population standard deviation, is known, right, when we don't know what mu is, but we do know what sigma is, our confidence interval is our best guess, which is the sample mean, plus or minus a margin of error. Now, mathematically we could show that the formula for that margin of error is something called z sub c times the standard deviation of the sample mean, right? So we center it at our best guess, and we add and subtract from that. We go away from that, essentially a certain number of standard deviations. How many standard deviations? Well, that's where the z sub c comes into play. Look at the very bottom of the slide. Z sub c is called the critical value of our confidence interval, and it depends on what level of confidence we want. What we'll see is the more confident we want to be, the larger that critical value will be, the more standard deviations out we need to go. Now remember, from the central limit theorem, the standard deviation of x bar is just the standard deviation of x over the square root of n. So that's our formula for a confidence interval for an unknown mean when we happen to know what the population standard deviation is. Here are some common critical values. Some commonly used critical values, probably the top 3 most commonly used, are 90% confidence is going to be 1.645. 95% confidence is 1.96. 99% confidence is 2.576. Now notice that 95% confidence is actually very close to what? It's very close to the number 2. These numbers essentially tie into that empirical rule, right? The empirical rule says that 95% of all observations are within 2 standard deviations of the mean, right? So if we want 95% confidence, we want a 95% chance of capturing the true mean, well, what we're basically saying is go, right, essentially 2 standard deviations out. We're not rounding quite as much when we use the 1.96. right? Which means that if we wanted to do, this is extremely uncommon and we wouldn't want to do it, but if we wanted a, say, 68% confidence interval, empirical rule tells us again that that would be essentially, our critical value would just be 1. We would go 1 standard deviation out to capture 68% of, right, the observations. So, just to reiterate, the big picture is this: to construct, to build, to make our confidence interval, we take our best guess for the population mean, which we spent the end of chapter 4 motivating and saying is the sample mean. We tack onto it, we add to it a margin of error. This margin of error depends on a number of things actually, but it particularly depends on our confidence level. As we observe, the margin of error is essentially saying go a certain number of standard deviations away from the sample mean. How many standard deviations, again, depends on your confidence. The more confident you want to be, the more standard deviations, the further you need to go out. So let's do an example. Let's say that we want to know the average jumping distance of kangaroos. Sure, we could just Google it or go to Wikipedia. It's true. But remember the rats. We've been burned by the internet before. So, if we wanted to really know, right, empirically know, statistically know how far on average kangaroos jump, what's the first thing that we would have to do that's easy to lose sight of, that's easy to lose track of in a sort of artificial classroom environment? The first thing we would have to do is we would have to take a sample, right? All conclusions in statistics have to be based off samples. So, let's say we go to kangaroos.com and we order same-day delivery 64 kangaroos. We have the 64 kangaroos delivered. We line them up on our front yard. We have a crazy fun kangaroo jumping Olympics. And at the end of the day, right, we take the jumping distance of each of the 64 kangaroos, we add them up, we divide by 64, we get the sample mean jumping distance. And that ends up being 25 feet. Moreover, let's say that, well, of course, everyone knows that the population standard deviation of jumping distance is 4 feet. So, let's go ahead and build a 90% confidence interval for the true but unknown mean jumping distance for all kangaroos. So here's the actual interval. The formula is x bar plus or minus, right, our critical value, z of 0.90, since we want a 90% confidence interval, times sigma over the square root of n. Right, all of those numbers, well, the 25, the 4, and the 64, I can get all of those from the setup of the problem. The 1.645 was like, what, 5 slides back? It was one of the commonly used critical values. For 90% confidence, we use a critical value of 1.645. So, our margin of error then is 0.8225. So our confidence interval is 25 plus or minus 0.8225. We're basically saying that we think the sample mean is within 0.8225 feet of the true mean. To get the actual confidence interval, right, the interval is a range of values. To get the actual confidence interval, we subtract 0.8225 from 25, and we add 0.8225 to 25, which gives us the interval. That's what those square brackets are saying. The square brackets are saying that our interval ranges from 24.1775 to 25.8225. We would then say that we are 90% confident that the true but unknown jumping distance of all kangaroos is somewhere between 24.1775 feet and 25.8225 feet. What about if I had asked us for a 95% confidence interval? Well, really the only thing that changes in that formula is that critical value. The 25, the 4, the 64, they stay the same. The only thing that changes is for 95% confidence, my critical value is going to be 1.96. So now it's 25 plus or minus 0.98, which gives me an interval from 24.02 to 25.98. We would say that we are 95% confident that the true but unknown jumping distance of all kangaroos is somewhere between 24.02 feet and 25.98 feet. Notice, by increasing the confidence from 90 to 95%, we've made the actual, well, the margin of error has gotten larger, and so correspondingly, the actual size of our interval has gotten larger.
So how do we do this on our highfalutin TI-83, TI-84 calculator? Well, the first thing we're going to do is we're going to hit the stats button. Of course, we're going to hit the stats button. This is the stats class. So the stats button is, look at the second key, go 2 to the right and 1 down, and there's the stats button. So hit the stats button. It's going to pull up some menus. Hit the right arrow until you're over the test menu. Of course we want the test menu because this would be pretty useful on a test. Then we're going to hit the down arrow, down, 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 down. We're going to go to Z interval, and we're going to select it by hitting the enter button on our calculator. Pulls up a new set of menus. Now, this may already have been done for you, depending on whether you're borrowing your calculator or not. But you want to make sure that the cursor is on the stats. It may not be. So where it has input, move it over to stats, select that by hitting enter. Now, you need to fill in a bunch of information. The next couple slides will show some screenshots of kind of what this should look like on your calculator, although hopefully these steps are easy enough to follow. So I'll talk you through a little bit about filling in this information. Once you've filled in that information, things like your confidence level, your sample mean, your population, standard deviation, and your sample size, I believe that's it. Once you've filled in all that information, you go down to the calculate option. Again, hit the enter key. Done and done.
So, here's what it looks like when you hit Z interval. Do you see that input option, that input line on the very top? By default, it starts, the cursor's on data. So that's why I said you got to move the cursor to stats and hit enter. Once you do that, you'll see a menu that looks like that. You'll see that little sigma symbol. That's the population standard deviation. You'll need to fill that in. So you'll hit the cursor down, you'll type in the number 4, and you'll hit enter. That will have a standard deviation of 4 now. And then you go down to the sample mean, that was 25. You go down to the sample size, that was 64. And then you go down to the confidence level. So I'm going to do the most recent one we did. I'm going to do the 95% confidence. Then you put your cursor over calculate and you hit enter. And this is what we see. It gives us the actual interval. And the interval is just like we determined ourselves. The interval goes from 24.02 to 25.98. Now, a couple big picture observations. You should sort of know these and be aware of these and hopefully understand them conceptually. I do like to put a few questions on the test that are kind of along these lines. When the confidence level increases, so does the margin of error. So what does that mean? It means that confidence comes at a cost. Right? We might wonder, why does the government settle for 95% confidence? Right? We pay good, hard-earned money on taxes to the government. We should, right, as citizens, be able to expect something better than 95% from our government. Why not? Well, we know you can't have a 100% confidence interval. In this world of uncertainty, you can never be 100% confident unless you sample the entirety of the population. But why not like 99.9999999% confidence? Well, the answer is right here in front of us. The more confident you want to be, the wider that margin of error ends up being. So if you made yourself, if you wanted to be something like 99.9999999% confident, your confidence interval would be something like negative 10 to 200 feet. You would say, well, I'm 99.9999999% confident that the true average jumping distance for all kangaroos is somewhere between negative 10 and 200 feet. And then, of course, people would roll their eyes and they would say, well, thanks for nothing. That was pretty useless. I didn't need your hoity-toity or highfalutin statistics to tell me that. right? So it's always a bit of a compromise. We do want to be confident. We'll talk a little bit about what it means to be confident, but right, intuitively, the more confident we are, the better, but at the same time we want our margin of error to be small. Right? And it's hard to have both because as we become more confident, our margin of error will increase. They have essentially, right, going back to our terminology from chapter 9, they have a positive relationship. What one does, the other does. The second observation is that if the standard deviation increases, so does the margin of error. Right? If you look at the formula for the margin of error, you can see this because the standard deviation is in the numerator. So making that standard deviation larger is going to make the overall margin of error larger. Again, standard deviation and margin of error have a positive relationship. What one does, the other does. One goes up, margin of error goes up, standard deviation goes down, margin of error goes down. This is fairly intuitive though, right? I mean, maybe the margin of error for how long it takes to get to Grandma's house is plus or minus 5 minutes. And let's say that they add a bunch of traffic lights between your house and Grandma's house. That's what? That's sort of effectively increased the variability. It's increased the uncertainty. It's increased the standard deviation for how long it takes to get from your house to Grandma's house, right? Because now there's more lights. You may or may not hit them red or green. And it is sort of intuitive, right? That if there's all these new traffic lights and there's this extra uncertainty, that I probably would no longer be saying plus or minus, say, 5 minutes. I would now say, well, now it's plus or minus 10 minutes. The last observation is this, and it's an important one. If the sample size increases, then the margin of error decreases, right? They have a negative relationship. We can see this, again, by looking at the formula for the margin of error. The formula for the margin of error has the sample size in the denominator. So as we already talked about, if you have a big number in the denominator, it makes the overall number small. This intuitively says large samples are good. That should make sense to us. Now notice, this is one of the things that a statistician or researcher has control over when they're doing a study, right? We determined how many kangaroos we wanted to actually order. This is a powerful observation because it in some ways sort of counteracts our first observation. Remember, we said the confidence comes at a cost. That is, if you want to have a higher confidence level, it makes your margin of error larger. Well, thankfully we have a way of then shrinking the margin of error. How can we then shrink the margin of error? We can get the margin of error as small as we want it to be by taking a large enough sample size. So, in theory, in reality, we could have any confidence level. We could have 99.99999% confidence and a margin of error as small as we want it to be by taking a large enough sample size. And it's really just some fairly basic math to determine what that sample size needs to be. Now, it may be that that sample size ends up being 10,000, and you say there's no way that I can order 10,000 kangaroos from kangaroos.com and line them up on my front yard. It may be that the sample size you need to obtain the confidence level you would like and the margin of error that you would like, it could be that that sample size is too cost prohibitive. In which case you're going to have to compromise. But in theory, you could have any confidence and any margin of error by taking a large enough sample size. Now, I hope, I've been wrong, I feel like, the last few times I've said this. I think this is our last slide, and it's really just discussing, right, what do we mean when we say 90% confident? What do we mean when we say 95% confident? Well, the confidence level C essentially gives us the probability that an interval will capture the true mean in repeated samples, right? One of the misstatements, one of the wrong statements, one of the false statements that that students or beginning researchers fairly often make is, right, going back to our kangaroo example, saying something like there's a 95% chance that the true mean is between, say, 24.02 and 25.98. That is not the correct way of interpreting it. The true mean is not a random variable. It's a parameter. It's a number. It's non-random, which means that it does not have a probability associated with it. The true mean is either in our interval, right, a fixed interval, our 24.02 and 25.98. The true mean is actually either between those numbers or not between those numbers. It's not maybe between those numbers. What the 95% confidence interval is saying is it's saying that if you repeated this process, if you ordered 64 kangaroos, had them all jump, made it a confidence interval, and then you did it again, you got a second different sample, got a different sample mean, and made a different confidence interval, and then did that a third time, a fourth time, a fifth time. If we did that, say, 1,000 times, we would expect 95% of these intervals to contain the true mean jumping distance of all kangaroos. So if we did it 1,000 times, we would expect roughly 950 of these intervals, right? Most of the intervals we would expect to contain the true mean. Now in reality, we just create one interval, and it's of course impossible for us to know whether the true mean is really in there or not. But we take solace, we take comfort knowing that we're using a process. We're using a procedure, right? That's what our confidence is in. Our confidence is in the procedure. We're using a procedure that most of the time gives an interval that will contain the true mean.